In this tutorial, we will use ScriptableObjects as a communication layer between game objects. This will be especially helpful when dealing with prefabs. To do this, we will use the following pattern. And like in the last tutorial, the black classes are classes provided by Unity, and the blue ones are the ones we will create. The event handle itself will be used as an event broadcaster, so that, for instance, an input controller only needs to know the corresponding event handle. The event listener controller then simply listens to the event handle and triggers certain behavior when the event handle is raised. Let's first reorganize our source code files. We will have two kinds of components, monoBehavior components and scriptable objects. We named our monoBehavior components controller, so we will create a corresponding folder. We will add another folder handles for our scriptable objects. Our tests will mirror this structure. Additionally, we also create a folder tools for our test tools. We will start by creating the event handle. The event handle will be very simple. It only has one event that we need to invoke. So let's create an event handle via ScriptableObject create instance, and then we will add an event listener, which will increment a counter. In our assertion, we will check this counter and see if it was incremented after we called raise. To satisfy the compiler, we just need to add the missing properties and methods to our event handle. The compiler complains that Onraise is never used, but this is fine for now. We run the test and recognize that it fails at our assertion. The implementation is straightforward. We simply invoke the Onraise event. And now the test passes. In C#, events without listeners will be null. Calling invoke on an empty handler therefore will throw an exception. We want to prevent that and add a corresponding test. The test asserts that no exception will be thrown when we call raise on an empty event handle. And as expected, this assertion fails. The canonical solution to this is simply adding a null check to the invoke statement. Now the test passes and our event handle is done already. Now we can add our event listener controller. In our first test, we will check the Onraise event. We will create an event listener controller and connect it with an event handler. We will then wait one frame and add a new behavior to our event listener, which, for simplicity's sake, simply increments a counter. The assertion then checks whether the counter has been incremented when we raise the event handler. I also added another test to make sure that the Unity event that we use for Onraise on the event listener has been initialized. Now we add the missing fields to our event listener controller. Both tests fail, but for different reasons. The first test fails due to an unexpected exception. The second test fails at our assertion. Let's first initialize our Onraise Unity event. The corresponding test now passes, while the other test finally fails at our assertion. In the start method, we will connect the event listener controller with the event handle. This test now passes. But the other test fails because the start method tries to access an event handle which is null. We could solve this via a null check. But in this case, I wanted this exception because the event listener controller only works with an event handle, and if I forget to set the event handle in the inspector, I want to see this exception. Which means I simply update the test and set an event handle. For brevity's sake, I will forego showing every time I run a test, but still make sure that during development you always follow the cycle of test, test fails, implementation, test succeeds. We add another check to make sure the component does not work when the game object is inactive. So we simply deactivate our game object, and we also assert that the counter is not incremented. After making sure the test fails at the expected assertion, we simply wrap our invocation with an activity check. After that succeeds, we add yet another check to make sure the component does not work when it is not enabled. So we simply disable our component and assert that the counter is not incremented. After making sure this also fails as expected, we add a check for the component activity. The next test makes sure that the component is removed from the event handle when the component or the game object is destroyed. This prevents potential resource leaks and should always be a consideration when working with events. In the test, we simply call object destroy on the whole game object. This time, we won't check against the counter because Unity will throw an exception when we call a method on a destroyed game object or a destroyed component. Instead, we will assert that no exception is thrown. After making sure the test failed at the accepted assertion, we use an implementation via the onDestroy method. And here we simply disconnect our event listener. After our tests passed, is now a good time to refactor our component. By using the onDisable method, we can achieve the same functionality but make our component way simpler. But now that we are using onDisable, we have to make sure that we reconnect our component when we re-enable it. The corresponding test will simply disable a component and in the next frame re-enable it, and we will check against the counter of 1. Similarly to onDisable, we will use onEnable for this implementation. But the test throws an unexpected exception. onEnable is already called during initialization, which means it is called when we use addComponent. At this moment we have not set an event handle, and thus we have a null exception. The simplest way to handle this is simply add a null check for the event handle. We also want to make sure that everything still works after we have, for some reason, reinitialized our Onraise Unity event. After we added an event listener, we will reinitialize the Unity event and assert a count of 0 because our new Unity event has no behavior attached. We implement this by connecting to the event handle via a dedicated raise method. And our last test will make sure that we are not connecting twice to the event handle when onUpdate and start are running in the same frame. We will simply deactivate our component in the frame we are initializing it. In the next frame, we re-enable it, which means that during this yield, start and onEnable will run at the same time. But we still assert a counter of 1. But running the test will show us that we have a count of 2 because we have connected twice. Adding a boolean to our component to keep track if it is connected or not will help us solve this. The boolean defaults to false. When we connect to the event handle, we set it to true, and when we disconnect, we set it to false. In dedicated methods for connecting and disconnecting, we simply check against this boolean. We will also set it to true when we have connected, and we will set it to false when we have disconnected. Now all the tests succeed and the component is done. In order to use the event handler in the editor, we need to create a menu item for it. We add a folder for ScriptableObjects, and then we add event handler for our directional movements. We can now create a prefab for our input, because the input controllers do not need to know who uses the input. We simply connect to the corresponding event handler. We reset the input in the scene, so it uses the same event handlers as the prefab. We will also combine our translation controllers with an event listener. The event listener will now trigger the translate fixed delta. We simply need to connect each event listener to its corresponding event handle. And now everything should work as it was before. We can also disable some of the game objects or the event listeners, and the corresponding movement direction should not work anymore. After re-enabling it, it should work again. It may seem like we haven't gained much value, but we are in the process of developing very powerful tools which will allow us to create plug-and-play style prefabs, so that in the future, by combining different game objects in different ways with each other, we can create vastly different and specialized behaviors without the need to write any additional code. But that's it for this tutorial. Next time we will create a scriptable object as a game object reference, so that we can create prefabs for our main camera and our movement directions. Let me know what you think, and thanks for watching.